More frequently, however, pyroclastic flows are generated by the collapse of tall eruption columns during an explosive event. When gravity eventually overcomes the initial upward thrust provided by the escaping gases, the ejected materials begin to fall, sending massive amounts of incandescent blocks, ash, and pumice cascading downslope. The destruction of St. Pierre. In 1902, an infamous pyroclastic flow and associated surge from Mount Pelee, a small volcano on the Caribbean island of Martinique, destroyed the port town of St. Pierre. Although the main pyroclastic flow was largely confined to the valley of Rivière Blanche, a low-density fiery surge spread south of the river and quickly engulfed the entire city. The destruction happened in moments and was so devastating that nearly all of St. Pierre's 28,000 inhabitants were killed. Only one person on the outskirts of town, a prisoner protected in a dungeon, and a few people on ships in the harbor were spared. St. Pierre as it appeared shortly after the eruption of Mount Pelee in 1902. B. St. Pierre before the eruption. Many vessels were anchored offshore when this photo was taken, as was the case on the day of the eruption. Figure 5.19 Destruction of St. Pierre. Scientists who arrived on the scene within days found that although St. Pierre was mantled by only a thin layer of volcanic debris, masonry walls nearly 1 meter thick had been knocked over like dominoes, large trees had been uprooted, and cannons had been torn from their mounts. The destruction of Pompeii. One well-documented event of historic proportions was the 79 eruption of the Italian volcano we now call Mount Vesuvius. For centuries prior to this eruption, Vesuvius had been dormant, with vineyards adorning its sunny slopes. Yet in less than 24 hours, the entire city of Pompeii and a few thousand of its residents were entombed beneath a layer of volcanic ash and pumice. The city and the victims of the eruption remained buried for nearly 17 centuries. The excavation of Pompeii gave archaeologists a superb picture of ancient Roman life. The ruins of the Roman city of Pompeii as they appear today. In less than 24 hours, Pompeii and all of its residents were buried under a layer of volcanic ash and pumice that fell like rain. B. Plaster casts of some of the victims of the eruption of Mount Vesuvius. Figure 5.20 Pompeii was excavated nearly 17 centuries after the 79 eruption of Mount Vesuvius. By reconciling historic records with detailed scientific studies of the region, volcanologists reconstructed the sequence of events. During the first day of the eruption, a rain of ash and pumice accumulated at a rate of 12 to 15 centimeters per hour, causing most of the roofs in Pompeii to eventually give way. Then, suddenly, a surge of searing hot ash and gas swept rapidly down the flanks of Vesuvius. This deadly pyroclastic flow killed those who had somehow managed to survive the initial ash and pumice fall. Their remains were quickly buried by falling ash, and subsequent rainfall caused the ash to harden. Over the centuries, the remains decomposed, creating cavities that were discovered by 19th-century excavators. Casts were then produced by pouring plaster of Paris into the voids. Mount Vesuvius has had more than 24 explosive eruptions since 79, the most recent occurring in 1944. Today, Vesuvius towers over the Naples skyline, a region occupied by roughly 3 million people. Such an image should prompt us to consider how volcanic crises might be managed in the future. Did you know? In 1902, when Mount Pelee erupted, the U.S. Senate was preparing to vote on the location of a canal connecting the Pacific and Atlantic Oceans. The choice was between Panama and Nicaragua, a country that featured a smoking volcano on its postage stamp. Supporters of the Panamanian route used the potential threat of volcanic eruptions in Nicaragua to bolster their argument in favor of Panama. The Senate subsequently approved the construction of the Panama Canal. In 2013, Nicaragua's National Assembly approved a bill to support the construction of a second canal connecting the Pacific Ocean and the Caribbean Sea to rival the Panama Canal. However, funding for this project has not been obtained. Lahars, mudflows on active and inactive cones. In addition to violent eruptions, large composite cones may generate a type of fluid mudflow, known by its Indonesian name, lahar. These destructive flows occur when volcanic debris becomes saturated with water and rapidly moves down steep volcanic slopes, generally following stream valleys. Some lahars are triggered when magma nears the surface of a glacially clad volcano, causing large volumes of ice and snow to melt. Others are generated when heavy rains saturate weathered volcanic deposits. Thus, lahars may occur even when a volcano is not erupting. When Mount St. Helens erupted in 1980, several lahars were generated. These flows and accompanying floodwaters race down nearby river valleys at speeds exceeding 30 km per hour. These raging rivers of mud destroyed or severely damaged nearly all the homes and bridges along their paths. Fortunately, the area was not densely populated. This lahar raced down the snow-covered slopes of Mount St. Helens following an explosive eruption on March 19, 1982. The aftermath of a lahar that formed following the 1982 eruption of Galunggung volcano, Indonesia. Figure 5.21 Lahars, mudflows that originate on volcanic slopes. In 1985, deadly lahars were produced during a small eruption of Nevado del Ruiz, a 5,300-meter volcano in the Andes Mountains of Colombia. Hot pyroclastic material melted ice and snow that capped the mountain and sent torrents of ash and debris down three major river valleys that flank the volcano. Reaching speeds of 100 km per hour, these mudflows tragically claimed 25,000 lives. Many consider Mount Rainier, Washington, to be America's most dangerous volcano because, like Nevado del Ruiz, it has a thick, year-round mantle of snow and glacial ice. Adding to the risk is the fact that more than 100,000 people live in the valleys around Rainier, and many homes are built on deposits left by lahars that flowed down the volcano hundreds or thousands of years ago. A future eruption, or perhaps just a period of heavier than average rainfall, may produce lahars that could be similarly destructive. Other volcanic hazards. Volcanoes can be hazardous to human health and property in other ways. Ash and other pyroclastic material can collapse the roofs of buildings or may be drawn into the lungs of humans and other animals or into aircraft engines. Volcanic gases, most notably sulfur dioxide, pollute the air and, when mixed with rainwater, can destroy vegetation and reduce the quality of groundwater. Despite the known risks, millions of people live in close proximity to active volcanoes. In addition to generating destructive pyroclastic flows and lahars, volcanoes can be hazardous to human health and property in many other ways. Figure 5.22 Volcanic hazards. Figure 5.22 Full alternative text description. Volcano-related tsunamis. Although tsunamis are most often associated with displacement along a fault located on the seafloor, some result from the collapse of a volcanic cone. This was dramatically demonstrated during the 1883 eruption on the Indonesian island of Krakatau, when the northern half of a volcano plunged into the Sunda Strait, creating a tsunami that exceeded 30 meters in height. Although Krakatau was uninhabited, an estimated 36,000 people were killed along the coastline of the islands of Java and Sumatra. Volcanic ash and aviation. During the past 20 years, at least 80 commercial jets have been damaged by inadvertently flying into clouds of volcanic ash. For example, in 1989, a Boeing 747 carrying more than 300 passengers encountered an ash cloud from Alaska's Redoubt volcano, all four engines clogged with ash and stalled midair. Fortunately, the pilots were able to restart the engines and safely landed the aircraft in Anchorage. More recently, the 2010 eruption of Iceland's geological volcano sent ash high into the atmosphere. This thick plume of ash drifted over Europe, causing airlines to cancel thousands of flights and leaving hundreds of thousands of travelers stranded. Several weeks passed before air travel resumed its normal schedule. Volcanic gases and respiratory health. One of the most destructive volcanic events, called the Loki eruptions, began along a large fissure in southern Iceland in 1783. An estimated 14 cubic kilometers of fluid basaltic lavas were released, along with 130 million tons of sulfur dioxide and other poisonous gases. When sulfur dioxide is inhaled, it reacts with moisture in the lungs to produce sulfuric acid, a deadly toxin. More than half of Iceland's livestock died, and the ensuing famine killed 25% of the island's human population. This huge eruption also endangered people and property all across Europe. Crop failure occurred in parts of Western Europe, and thousands of residents perished from lung-related diseases. One report estimated that a similar eruption today would cause more than 140,000 cardiopulmonary fatalities in Europe alone. Effects of volcanic ash and gases on weather and climate. Volcanic eruptions can eject dust-sized particles of volcanic ash and sulfur dioxide gas high into the atmosphere. The ash particles reflect sunlight back to space, producing temporary atmospheric cooling. The 1783 Loki eruptions in Iceland appear to have affected atmospheric circulation around the globe. Drought conditions prevailed in the Nile River Valley in India, and the winter of 1784 saw the longest period of below-zero temperatures in New England's history. Other eruptions that have produced significant effects on climate worldwide include the eruption of Indonesia's Mount Tambora in 1815, which produced the year without a summer, and the eruption of El Chichon in Mexico in 1982. El Chichon's eruption, although small, emitted an unusually large quantity of sulfur dioxide that reacted with water vapor in the atmosphere to produce a dense cloud of tiny sulfuric acid droplets. Such particles, called aerosols, take several years to settle out of the atmosphere. Like fine ash, these aerosols lower the mean temperature of the atmosphere by reflecting solar radiation back to space. Concept checks 5.8. 1. Describe pyroclastic flows and explain why they are capable of traveling great distances. 2. What is a lahar? 3. List at least 3 volcanic hazards besides pyroclastic flows and lahars. 5.9 Other volcanic landforms. List volcanic landforms other than shield, cinder cone, and composite volcanoes and describe their formation. The most widely recognized volcanic structures are the cone-shaped edifices of composite volcanoes that dot Earth's surface. However, volcanic activity produces other distinctive and important landforms. Calderas. Recall that calderas are large steep-sided depressions that have diameters exceeding 1 kilometer and have a somewhat circular form. Those that are less than 1 kilometer across are called collapse pits, or craters. Most calderas are formed by one of the following processes: the collapse of the summit of a large composite volcano following an explosive eruption of silica-rich pumice and ash fragments, the collapse of the top of a shield volcano caused by subterranean drainage from a central magma chamber, and the collapse of a large area, caused by the discharge of colossal volumes of silica-rich pumice and ash along ring fractures. Crater Lake, type calderas. Crater Lake, Oregon, is situated in a caldera approximately 10 kilometers wide and 600 meters deep. This caldera formed about 7,000 years ago, when a composite cone named Mount Mazama violently extruded 50 to 70 cubic kilometers of pyroclastic material, figure 5. 23. With the loss of support, 1,500 meters of the summit of this once prominent cone collapsed, producing a caldera that eventually filled with water. Later, volcanic activity built a small cinder cone in the caldera. Today this cone, called Wizard Island, provides a mute reminder of past activity. Smart Figure 5.23 Formation of Crater Lake, type calderas. About 7,000 years ago, a violent eruption partly emptied the magma chamber of former Mount Mazama, causing its summit to collapse. Precipitation and groundwater contributed to forming Crater Lake, the deepest lake in the United States, 600 meters deep, and the 9th deepest in the world. Smart Figure 5.23 Full Alternative Text Description. Watch animation, Formation of a caldera. Hawaiian-type calderas. Unlike Crater Lake type calderas, many calderas form gradually because of the loss of lava from a shallow magma chamber underlying a volcano's summit. For example, Hawaii's active shield volcanoes, Mauna Loa and Kilauea, both have large calderas at their summits. Kilauea's measures 3.3 by 4.4 kilometers and is 150 meters deep. The walls are almost vertical, and as a result, the caldera looks like a vast, nearly flat-bottomed pit. Kilauea's caldera formed by gradual subsidence as magma slowly drained laterally from the underlying magma chamber, leaving the summit unsupported. Yellowstone-type calderas. Historic and destructive eruptions such as Mount St. Helens pale in comparison to what happened 630,000 years ago in the region now occupied by Yellowstone National Park, when approximately 1,000 cubic kilometers of pyroclastic material erupted. This catastrophic eruption sent showers of ash as far as the Gulf of Mexico and formed a caldera 70 kilometers across. Vestiges of this event are the many hot springs and geysers in the Yellowstone region. This map shows Yellowstone National Park and the location and size of the Yellowstone caldera. Three huge eruptions, separated by relatively regular intervals of about 700,000 years, were responsible for the ash layers shown. The largest of these eruptions was 10,000 times greater than the 1980 eruption of Mount St. Helens. Smart Figure 5.24 Full Alternative Text Description. Smart Figure 5.24 Supereruptions at Yellowstone. Yellowstone-type eruptions eject huge volumes of pyroclastic materials, mainly in the form of ash and pumice fragments. Typically, these materials are ejected as pyroclastic flows that sweep across the landscape, destroying most living things in their paths. Upon coming to rest, the hot fragments of ash and pumice fuse together, forming a welded tuff that closely resembles a solidified lava flow. Despite the immense size of these calderas, the eruptions that produce them are brief, lasting hours to perhaps a few days. Large calderas tend to exhibit a complex eruptive history. In the Yellowstone region, for example, 3 caldera-forming episodes are known to have occurred over the past 2.1 million years. The most recent eruption was followed by episodic outpourings of degassed rhyolitic and basaltic lavas. In the intervening years, a slow upheaval of the floor of the caldera has produced 2 elevated regions called resurgent domes. A recent study has determined that a huge magma reservoir still exists beneath Yellowstone. Thus, another caldera-forming eruption is likely, but not necessarily imminent. Watch tutorial, Yellowstone caldera. Unlike calderas associated with shield volcanoes or composite cones, Yellowstone-type calderas are so vast and poorly defined that many were undetected until high-quality aerial and satellite images became available. Other examples of Yellowstone-type calderas are California's Long Valley Caldera, La Guarita Caldera, located in the San Juan Mountains of southern Colorado, and the Valles Caldera, west of Los Alamos, New Mexico. These and similar calderas found around the globe are among the largest volcanic structures on Earth, hence the name supervolcanoes. Volcanologists compare their destructive force to that of the impact of a small asteroid. Fortunately, no Yellowstone-type eruption has occurred in historic times. Fissure eruptions and basalt plateaus. The greatest volume of volcanic material is extruded from fractures in Earth's crust, called fissures. Rather than building cones, fissure eruptions usually emit fluid basaltic lavas that blanket wide areas. In some locations, extraordinary amounts of lava have been extruded along fissures in a relatively short time, geologically speaking. These voluminous accumulations are commonly referred to as basalt plateaus because most have a basaltic composition and tend to be rather flat and broad. The Columbia Plateau in the northwestern United States, which consists of the Columbia River basalts, is a product of this type of activity. Numerous fissure eruptions have buried the landscape, creating a lava plateau nearly 1,500 meters thick. Some of the lava remained molten long enough to flow 150 kilometers from its source. The term flood basalts appropriately described these extrusions. Lava founaining from a fissure and formation of fluid lava flows called flood basalts. The lower photo shows flood basalt flows near Idaho Falls. The Columbia River basalts cover an area of nearly 164,000 square kilometers that is commonly called the Columbia Plateau. Activity here began about 17 million years ago, as lava began to pour out of large fissures, eventually producing a basalt plateau with an average thickness of more than 1 kilometer. Columbia River basalt flows exposed in the Palouse River Canyon in southwestern Washington state. Figure 5.25 Basaltic fissure eruptions. Figure 5.26 Columbia River basalts. Figure 5.26 Full alternative text description. Massive accumulations of basaltic lava, similar to those of the Columbia Plateau, occur elsewhere in the world. One of the largest is known as the Deccan Plateau or Deccan Traps, a thick sequence of flat-lying basalt flows covering nearly 500,000 square kilometers of west-central India. When the Deccan Traps formed about 66 million years ago, nearly 2 million cubic kilometers of lava were extruded over a period of approximately 1 million years. Several other massive accumulations of flood basalts, including the Ontong Java Plateau, have been discovered in the deep ocean basins. Lava domes. In contrast to hot basaltic lavas, cool silica-rich rhyolitic lavas are so viscous that they hardly flow at all. As the thick lava is squeezed out of a vent, it often produces a dome-shaped mass called a lava dome. Lava domes are usually only a few tens of meters high, and they come in a variety of shapes that range from pancake-like flows to steep-sided plugs that were pushed upward like pistons. Most lava domes grow over a period of several years, following an explosive eruption of silica-rich magma. A recent example is the dome that began to grow in the crater of Mount St. Helens immediately following the 1980 eruption. This lava dome began to develop in the vent of Mount St. Helens following the May 1980 eruption. The collapse of a lava dome often results in a powerful pyroclastic flow. Figure 5.27 Lava domes can generate pyroclastic flows. Figure 5.27 Full alternative text description. Collapsing lava domes, particularly those that form on the summit or along the steep flanks of composite cones, often produce powerful pyroclastic flows. These flows result from highly viscous magma slowly entering the dome, causing it to expand and steepen its flanks. Over time, the cooler outer layer of the dome may start to crumble, producing relatively small pyroclastic flows consisting of dense blocks of lava. Occasionally, the rapid removal of the outer layer causes a significant decrease in pressure on the hot gaseous magma in the interior of the dome. Explosive degassing of the interior magma then triggers a fiery pyroclastic flow that races down the flanks of the volcano. Since 1995, pyroclastic flows generated by the collapse of several lava domes on Soufriere Hills volcano have rendered more than half of the Caribbean island of Montserrat uninhabitable. The capital city, Plymouth, was destroyed, and 2/3 of the population has evacuated. In 1991, a collapsed lava dome at the summit of Japan's Mount Unzen produced a pyroclastic flow that claimed 44 lives. Many of the victims were journalists and filmmakers who ventured too close to the volcano in order to obtain photographs and document the event. Volcanic necks. Most of the lava and materials erupted from a volcano travel through short conduits that connect shallow magma chambers to vents located at the surface. When a volcano becomes inactive, congealed magma is often preserved in the feeding conduit of the volcano as a crudely cylindrical mass. As the volcano succumbs to forces of weathering and erosion, the rock occupying the volcanic conduit, which is highly resistant to weathering, may remain standing above the surrounding terrain long after the cone has been worn away. Shiprock, New Mexico, is a widely recognized and spectacular example of these structures, which geologists call volcanic necks. More than 510 meters high, Shiprock is taller than most skyscrapers and is one of many such landforms that protrude conspicuously from the red desert landscapes of the American Southwest. Smart Figure 5.28 Volcanic Neck. Shiprock, New Mexico, is a volcanic neck that stands about 520 meters high. It consists of igneous rock that crystallized in the vent of a volcano that has long since been eroded. Smart Figure 5.28 Full Alternative Text Description. Watch Tutorial, Shiprock. Concept Checks 5.9. One, describe the formation of Crater Lake. Compare it to the calderas found on shield volcanoes such as Kilauea. 2. Other than composite volcanoes, what volcanic landform can generate a pyroclastic flow? 3. How do the eruptions that created the Columbia Plateau differ from the eruptions that create large composite volcanoes? 4. What type of volcanic structure is Shiprock, New Mexico, and how did it form? 5.10 Plate tectonics and volcanism. Explain how the global distribution of volcanic activity is related to plate tectonics. Geologists have known for decades that the global distribution of most of Earth's volcanoes is not random. Most active volcanoes on land are located along the margins of the ocean basins, notably within the circum-Pacific belt known as the Ring of Fire, where denser oceanic lithosphere subducts under continental lithosphere. Another group of volcanoes includes the innumerable seamounts that form along the crest of the mid-ocean ridges. There are some volcanoes, however, that appear to be randomly distributed around the globe. These volcanic structures comprise most of the islands of the deep ocean basins, including the Hawaiian Islands, the Galapagos Islands, and Easter Island. Figure 5.29 Ring of Fire. Most of Earth's major volcanoes are located in a zone around the Pacific called the Ring of Fire. Another large group of active volcanoes lie unseen along the mid-ocean ridge system. Figure 5.29 Full Alternative Text Description. The development of the theory of plate tectonics provided geologists with a plausible explanation for the distribution of Earth's volcanoes and established the basic connection between plate tectonics and volcanism. Plate motions provide the mechanisms by which mantle rocks undergo partial melting to generate magma. Volcanism at divergent plate boundaries. The greatest volume of magma erupts along divergent plate boundaries associated with seafloor spreading, out of human sight. Below the ridge axis where lithospheric plates are continually being pulled apart, the solid yet mobile mantle rises to fill the rift. Recall that as hot rock rises, it experiences a decrease in confining pressure and may undergo decompression melting. This activity continuously adds new basaltic rock to plate margins, temporarily welding them together, only to have them break again as spreading continues. Along some ridge segments, extrusions of pillow lavas build numerous volcanic structures, the largest of which is Iceland. Smart Figure 5.30 Earth Zones of Volcanism. Smart Figure 5.30 Full Alternative Text Description. Figure 5.11-1 Full Alternative Text Description. Watch Tutorial, Plate Tectonics and Volcanoes. Although most spreading centers are located along the axis of an oceanic ridge, some are not. In particular, the East African Rift is a site where continental lithosphere is being pulled apart. Vast outpourings of fluid basaltic lavas as well as several active volcanoes are found in this region of the globe. Volcanism at convergent plate boundaries. Recall that along convergent plate boundaries, two plates move toward each other, and a slab of dense oceanic lithosphere descends into the mantle. In these settings, water driven from hydrated minerals found in the subducting oceanic crust and overlying sediments triggers partial melting in the hot mantle above. Volcanism at a convergent plate margin results in the development of a slightly curved chain of volcanoes called a volcanic arc. These volcanic chains develop roughly parallel to the associated trench at distances of 200 to 300 kilometers. Volcanic arcs that develop within the ocean and grow large enough for their tops to rise above the surface are labeled archipelagos in most atlases. Geologists prefer the more descriptive term volcanic island arcs, or simply island arcs. Several young volcanic island arcs border the western Pacific Basin, including the Aleutians, the Tongas, and the Marianas. Did you know? At 4,392 m in altitude, Washington's Mount Rainier is the tallest of the 15 great volcanoes that make up the backbone of the Cascade Range. Although Mount Rainier is considered an active volcano, its summit is covered by more than 25 alpine glaciers. Volcanism associated with convergent plate boundaries may also take place where slabs of oceanic lithosphere are subducted under continental lithosphere to produce a continental volcanic arc. The mechanisms that generate these mantle-derived magmas are essentially the same as those that create volcanic island arcs. The most significant difference is that continental crust is much thicker and composed of rocks having higher silica content than oceanic crust. Hence, by melting the surrounding silica-rich crustal rocks, mantle-derived magma changes composition as it rises through the crust. The volcanoes of the Cascade Range in the northwestern United States, including Mount Hood, Mount Rainier, Mount Shasta, and Mount St. Helens, are examples of volcanoes generated at a convergent plate boundary along a continental margin. Smart Figure 5.31 Subduction-produced Cascade Range volcanoes. Subduction of the Juan de Fuca plate along the Cascadia subduction zone produced the Cascade volcanoes. Smart Figure 5.31 Full alternative text description. Watch tutorial, The Cascade Range. Intraplate volcanism. We know why igneous activity is initiated along plate boundaries, but why do eruptions occur in the interiors of plates? Hawaii's Kilauea, considered one of the world's most active volcanoes, is situated thousands of kilometers from the nearest plate boundary, in the middle of the vast Pacific Plate. Figure 5. 30C. Sites of intraplate volcanism include the large outpourings of fluid basaltic lavas such as those that compose the Columbia Plateau, the Siberian Traps in Russia, India's Deccan Plateau, and several submerged oceanic plateaus, including the Ontong Java Plateau in the western Pacific. The basalt plateaus are thought to be the product of a burst of volcanism generated by partial melting of the bulbous head of a hot mantle plume. The orange dashed lines represent the chain of volcanic structures produced by partial melting of the plume tail. The orange dots are thought to be the current surface locations of the hot mantle plumes that generated the associated basalt plateaus. Smart Figure 5.32 Global distribution of large basalt provinces. Smart Figure 5.32 Full alternative text description. Watch tutorial, Hotspots and flood basalts. Most intraplate volcanism occurs when a relatively narrow mass of hot mantle plume ascends toward the surface. Although the depth at which mantle plumes originate is a topic of debate, some are thought to form deep within Earth, at the core, mantle boundary. These plumes of solid yet mobile rock rise toward the surface in a manner similar to the blobs that form within a lava lamp. Such a lamp contains two immiscible liquids in a glass container, and as the base of the lamp is heated, the denser liquid at the bottom becomes buoyant and forms blobs that rise to the top. Like the blobs in a lava lamp, a mantle plume has a bulbous head that draws out a narrow stalk beneath it as it rises. The surface manifestation of this activity is called a hot spot, an area of volcanism, high heat flow, and crustal uplifting a few hundred kilometers wide. Some geologists question the role of mantle plumes in the formation of Earth's volcanic landforms. Model of hotspot volcanism thought to explain the formation of large basalt plateaus and the chains of volcanic islands associated with these. Features: Figure 5.33 Mantle plumes and large basalt provinces. Figure 5.33 Full alternative text description. Large mantle plumes, dubbed superplumes, are thought to be responsible for the vast outpourings of basaltic lava that created the large basalt plateaus. When the head of the plume reaches the base of the lithosphere, decompression melting progresses rapidly. This causes the burst of volcanism that emits voluminous flows of lava over a period of 1 million or so years. Extreme eruptions of this type would have affected Earth's climate, causing the extinction events recorded in the fossil record. The comparatively short initial eruptive phase is often followed by millions of years of less voluminous activity, as the plume tail slowly rises to the surface. Extending away from some large flood basalt plateaus is a chain of volcanic structures, similar to the Hawaiian chain. Intraplate volcanism associated with mantle plumes is also thought to be responsible for the massive eruptions of silica-rich pyroclastic material that occurred in continental settings. Perhaps the best known of these hotspot eruptions are the 3 caldera-forming eruptions that occurred in the Yellowstone region over the past 2.1 million years. Concept checks 5.10. 1. Are volcanoes in the Ring of Fire generally described as effusive or explosive? Provide an example that supports your answer. 2. How is magma generated along convergent plate boundaries? 3. Volcanism at divergent plate boundaries is most often associated with which magma type? What causes rocks to melt in these settings? 4. What is thought to be the source of magma for most intraplate volcanism? 5. Which type of plate boundary generates the greatest quantity of magma? Concepts in review: volcanoes and volcanic hazards. 5.1 Mount St. Helens versus Kilauea. Compare and contrast the 1980 eruption of Mount St. Helens with the most recent eruption of Kilauea, which began in 1983. Volcanic eruptions cover a broad spectrum from explosive eruptions, like that of Mount St. Helens in 1980, to the quiescent eruptions of Kilauea. 5.2 The nature of volcanic eruptions. Explain why some volcanic eruptions are explosive and others are quiescent. Key terms: magma lava, effusive eruption, viscosity eruption column. The two primary factors determining the nature of a volcanic eruption are the viscosity of the magma and its gas content. In general, magmas that contain more silica are more viscous, while those with lower silica content are more fluid. Temperature also influences viscosity. Hot lavas are more fluid, while cool lavas are more viscous. Basaltic magmas, which are fluid and have low gas content, tend to generate effusive eruptions. In contrast, silica-rich magmas, which are the most viscous and contain the greatest quantity of gases, are the most explosive. Although Kilauea mostly erupts in a gentle manner, what risks might you encounter if you chose to live nearby? 5.3 Materials extruded during an eruption. List and describe the 3 categories of materials extruded during volcanic eruptions. Key terms: AA flow, pahoehoe flow, lava tube, pillow lava, block lava, volatile. Pyroclastic material, tephra, scoria, pumice. Volcanoes erupt molten lava, gases, and solid pyroclastic materials. Low-viscosity basaltic lava flows can extend great distances from a volcano. On the surface, they travel as pahoehoe or AA flows. Sometimes the surface of the flow congeals, and lava continues to flow below in tunnels called lava tubes. When lava erupts. Underwater, the outer surface is chilled instantly to obsidian, while the inside continues to flow, producing pillow lavas. The gases most commonly emitted by volcanoes are water vapor and carbon dioxide. Upon reaching the surface, these gases rapidly expand, leading to explosive eruptions that can generate a mass of lava fragments called pyroclastic materials. Pyroclastic materials come in several sizes. From smallest to largest, they are ash, lapilli, and blocks or bombs. Blocks exit the volcano as solid fragments, whereas bombs exit as liquid blobs. If bubbles of gas and lava don't pop before the lava solidifies, they are preserved as voids called vesicles. Especially frothy, silica-rich lava can cool to make lightweight pumice, while basaltic lava with lots of bubbles cools to make scoria. This photo shows layers of volcanic material ejected by a violent eruption and deposited roughly horizontally. What term is used to describe this type of volcanic material? 5.4 Anatomy of a volcano. Draw and label a diagram that illustrates the basic features of a typical volcanic cone. Key terms: fissure conduit vent volcanic cone crater caldera parasitic cone fumarole. Volcanoes vary in size and form but share a few common features. Most are roughly conical piles of extruded material that collect around a central vent. The vent is usually within a summit crater or caldera. On the flanks of the volcano, there may be smaller vents marked by small parasitic cones, or there may be fumaroles, spots where gas is expelled. Label the diagram using the following terms: conduit, vent, lava, parasitic cone, bombs, pyroclastic material. Figure 5.12-1 Full alternative text description. 5.5 Shield volcanoes. Summarize the characteristics of shield volcanoes and provide one example of this type of volcano. Key terms: shield volcano seamount. Shield volcanoes consist of many successive lava flows of low-viscosity basaltic lava but lack significant amounts of pyroclastic debris. Lava tubes help transport lava far from the main vent, resulting in very gentle, shield-like profiles. Most shield volcanoes begin as seamounts that grow from Earth's seafloor. Mauna Loa, Mauna Kea, and Kilauea in Hawaii are classic examples of the low, wide-form characteristic of shield volcanoes. 5.6 Cinder cones. Describe the formation, size, and composition of cinder cones. Key terms: cinder cone. Cinder cones are steep-sided structures composed mainly of pyroclastic debris, typically having a basaltic composition. Lava flows sometimes emerge from the base of a cinder cone but typically do not flow out of the crater. Cinder cones are small relative to the other major kinds of volcanoes, reflecting the fact that most form quickly, as single eruptive events. Because they are unconsolidated, cinder cones easily succumb to weathering and erosion. 5.7 Composite volcanoes. List the characteristics of composite volcanoes and describe how they form. Key term: composite volcano. Composite volcanoes are called composite because they consist of both pyroclastic material and lava flows. They typically erupt silica-rich magmas of andesitic or rhyolitic composition. They are much larger than cinder cones and form from multiple eruptions over millions of years. Because andesitic and rhyolitic lavas are more viscous than basaltic lava, they accumulate at a steeper angle than does the lava from shield volcanoes. Over time, a composite volcano's combination of lava and cinders produces a towering volcano with a classic symmetrical shape. Mount Rainier and the other volcanoes of the Cascade Range in the northwest United States are good examples of composite volcanoes. If your family had to live next to a volcano, would you rather it be a shield volcano, cinder cone, or composite volcano? Explain. 5.8 Volcanic hazards. Describe the major geologic hazards associated with volcanoes. Key terms. Pyroclastic flow lahar tsunami. The greatest volcanic hazard to human life is the pyroclastic flow, or nuée ardente. This dense mix of hot gas and pyroclastic fragments races downhill at great speed and incinerates everything in its path. A pyroclastic flow can travel many kilometers from its source volcano. Because pyroclastic flows are hot, their deposits frequently weld together into a solid rock called welded tuff. Lahars are mud flows that form on volcanoes. These rapidly moving slurries of ash and debris suspended in water tend to follow stream valleys and can result in loss of life and/or significant damage to structures. Volcanic ash in the atmosphere can be a risk to air travel when it is sucked into airplane engines. Volcanoes at sea level can generate tsunamis when they erupt or when their flanks collapse into the ocean. Those that spew large amounts of gas such as sulfur dioxide can cause respiratory problems. If volcanic gases reach the stratosphere, they screen out a portion of incoming solar radiation and can trigger short-term cooling at Earth's surface. What phenomenon is illustrated in the accompanying image? 5.9 Other volcanic landforms. List volcanic landforms other than shield, cinder cone, and composite volcanoes and describe their formation. Key terms. Fissure eruption basalt plateau flood basalt lava dome volcanic neck. Calderas, which can be among the largest volcanic structures, form when the rigid, cold rock above a magma chamber cannot be supported and collapses, creating a broad, roughly circular depression. On shield volcanoes, calderas form slowly as lava drains from the magma chamber beneath the volcano. On a composite volcano, caldera collapse often follows an explosive eruption that can result in significant loss of life and destruction of property. Fissure eruptions occasionally produce massive floods of fluid basaltic lava from large cracks, called fissures, in the crust. Layer upon layer of these flood basalts may accumulate to significant thicknesses and blanket a wide area. The Columbia Plateau located in the northwestern United States is an example. Lava domes are thick masses of high viscosity, silica-rich lava that accumulate in the summit crater or caldera of a composite volcano. When they collapse, lava domes can produce extensive pyroclastic flows. Shiprock, New Mexico, is an example of a volcanic neck where the lava in the throat of an ancient volcano crystallized to form a plug of solid rock that weathered more slowly than the surrounding volcanic rocks. The surrounding pyroclastic debris eroded, and the resistant neck remains as a distinctive landform. 5.10 Plate tectonics and volcanism. Explain how the global distribution of volcanic activity is related to plate tectonics. Key terms. Ring of fire. Volcanic island arc, continental volcanic arc, intraplate volcanism, mantle plume, hotspot superplume. Volcanoes occur at both convergent and divergent plate boundaries, as well as in intraplate settings. At divergent plate boundaries, where lithosphere is being rifted apart, decompression melting is the dominant generator of magma. As warm rock rises, it can begin to melt without the addition of heat. Convergent plate boundaries that involve the subduction of oceanic crust are the most common site for explosive volcanoes, most prominently in the Pacific Ring of Fire. The release of water from the subducting plate triggers melting in the overlying mantle. The ascending magma interacts with the lower crust of the overlying plate and can form a volcanic arc at the surface. In intraplate settings, the source of magma is a mantle plume, a column of mantle rock that is warmer and more buoyant than the surrounding mantle. The accompanying diagram shows one of the tectonic settings where volcanism is a dominant process. Name the tectonic setting and briefly explain how magma is generated in this setting. Give it some thought. 1. Examine the accompanying photo and complete the following. A. What type of volcano is it? What features helped you classify it as such? B. What is the eruptive style of such volcanoes? Describe the likely composition and viscosity of its magma. C. Which type of plate boundary is the likely setting for this volcano? D. Name a city that is vulnerable to the effects of a volcano of this type. 2. Answer the following questions about divergent boundaries, such as the Mid-Atlantic Ridge and their associated lavas. Divergent boundaries are characterized by eruptions of what type of lava: andesitic, basaltic, or rhyolitic? B. What is the main source of the lavas that erupt at divergent plate boundaries? C. What process causes the source rocks to melt? 3. For each of the volcanoes or volcanic regions listed below, identify whether it is associated with a convergent or divergent plate boundary or with intraplate volcanism. A. Crater Lake. B. Hawaii's Kilauea. C. Mount St. Helens. D. East African Rift. E. Yellowstone. F. Mount Pelee. G. Deccan Traps. H. Fujiyama. 4. For each of the accompanying 4 sketches, identify the geologic setting. Which of these settings will most likely generate explosive eruptions? Which will produce outpouring of fluid basaltic lavas? Figure 5.12-1 full alternative text description. 5. Explain why an eruption of Mount Rainier similar to the 1980 eruption of Mount St. Helens could be considerably more destructive. 6. This image shows the Buddhist monastery Tong Kalat, located in central Myanmar. The monastery sits high on a sheer-sided rock made mainly of magmas that solidified in the conduit of an ancient volcano. The volcano has since been worn away. Based on this information, what igneous structure do you think is shown in this photo? B. Would this volcanic structure most likely have been associated with a composite volcano or a cinder cone? Explain how you arrived at your answer. 7. The formula for the volume of a cone is V equals 1/3 pi r2h. If Mauna Loa is 9 kilometers high and has a radius of roughly 85 kilometers, what is its approximate total volume? 8. The accompanying image shows a geologist at the end of an unconsolidated flow consisting of lightweight lava blocks that rapidly descended the flank of Mount St. Helens. What term best describes this type of flow: an AA flow, a Pahoehoe flow, or a pyroclastic flow? B. What lightweight igneous rock type is likely the main constituent of this flow? 9. Different processes produce magma in different tectonic settings. Consider magma bodies found at locations A, B, and C in the accompanying diagram and describe the process that most likely triggered the melting that produced each. Figure 5.12-1 full alternative text description. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, and the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 6: Weathering and Soils. Weathering processes helped shape the rock formations in California's Pinnacles National Park. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 6.1 Define weathering and distinguish between the two main categories of weathering. 6.2 List and describe 4 examples of mechanical weathering. 6.3 Discuss the importance of water and carbonic acid in chemical weathering processes. 6.4 Summarize the factors that influence the type and rate of rock weathering. 6.5 Define soil and explain why soil is referred to as an interface. List and briefly discuss 5 controls of soil formation. 6.6 Sketch, label, and describe an idealized soil profile. Explain the need for classifying soils. 6.7 Explain the detrimental impact of human activities on soil. 6.8 Relate weathering to the formation of certain ore deposits. Earth's surface is constantly changing. Rock is disintegrated and decomposed, moved to lower elevations by gravity, and carried away by water, wind, or ice. In this manner, Earth's physical landscape is sculpted. This chapter focuses on the first step of this never-ending process, weathering. It looks at what causes solid rock to crumble and why the type and rate of weathering vary from place to place. Soil, an important product of the weathering process and a vital resource, is also examined. 6.1 Weathering. Define weathering and distinguish between the two main categories of weathering. Weathering involves the physical breakdown and chemical alteration of rock at or near Earth's surface. Weathering goes on all around us, but it is such a slow and subtle process that its importance is easy to underestimate. Yet weathering is a basic part of the rock cycle and thus a key process in the Earth system. Weathering is also important to humans, even to those of us who are not studying geology. For example, many of the life-sustaining minerals and elements found in soil, and ultimately in the food we eat, were freed from solid rock by weathering processes. As the chapter opening photo, Figure 6.1, and many other images in this book illustrate, weathering also contributes to the formation of some of Earth's most spectacular scenery. Of course, these same processes are also responsible for causing the deterioration of many of the structures we build. Mechanical and chemical weathering contributed greatly to the creation of North Window Arch and to all of the other arches and rock formations in Utah's Arches National Park. Smart Figure 6.1 Arches National Park. Watch animation, Arches National Park. There are 2 basic categories of weathering. Mechanical weathering is accomplished by physical forces that break rock into smaller and smaller pieces without changing the rock's mineral composition. Chemical weathering involves a chemical transformation of rock into one or more new compounds. These 2 concepts can be illustrated with a large log. The log disintegrates when it is split into smaller and smaller pieces, whereas decomposition occurs when the log is set afire and burned. Why does rock weather? Simply, weathering is the response of Earth materials to a changing environment. For instance, after millions of years of uplift and erosion, the rocks overlying a large, intrusive igneous body may be removed, exposing it at the surface. This mass of crystalline rock, formed deep below ground, where temperatures and pressures are high, is now subjected to a very different and comparatively hostile surface environment. In response, this rock mass will gradually change. This transformation of rock is what we call weathering. In the following sections, we will examine the various types of mechanical and chemical weathering. Although we will consider these two categories separately, keep in mind that mechanical and chemical weathering processes usually work simultaneously in nature and reinforce each other. Concept checks 6.1. 1. What are the two basic categories of weathering? 2. How do the products of each category of weathering differ? 6.2 Mechanical weathering. List and describe 4 examples of mechanical weathering. When a rock undergoes mechanical weathering, it is broken into smaller and smaller pieces, each retaining the characteristics of the original material. The end result is many small pieces from a single large one. Figure 6. 2 shows that breaking a rock into smaller pieces increases the surface area available for chemical attack. An analogous situation occurs when sugar is added to a liquid. A sugar cube dissolves much more slowly than an equal volume of sugar granules because the cube has much less surface area available for dissolution. Hence, by breaking rocks into smaller pieces, mechanical weathering increases the amount of surface area available for chemical weathering. Smart Figure 6.2 Mechanical weathering increases surface area. Mechanical weathering adds to the effectiveness of chemical weathering because chemical weathering can occur only on exposed surfaces. Smart Figure 6.2 Full alternative text description. Watch tutorial, Physical and chemical weathering. In nature, for physical processes are mainly responsible for fragmenting rock, frost wedging, salt crystal growth, sheeting, and biological activity. In addition, although the work of erosional agents such as wind, waves, glacial ice, and running water is usually considered separately from mechanical weathering, this work is nevertheless related. As these mobile agents transport rock debris, particles continue to be broken and abraded. Did you know? The intense heat from a brush or forest fire can cause flakes of rock to break from boulders or bedrock. As the rock surface becomes overheated, a thin layer expands and shatters. Frost wedging. If you leave a glass bottle of water in the freezer a bit too long, you will find the bottle fractured, as in Figure 6.3. The bottle breaks because liquid water has the unique property of expanding about 9% upon freezing. This is also the reason that poorly insulated or exposed water pipes rupture during frigid weather. You might also expect the same process to fracture rocks in nature. This is, in fact, the basis for the traditional explanation of frost wedging. After water works its way into the cracks in rock, the freezing water enlarges the cracks, and angular fragments break off. The bottle broke because water expands about 9% when it freezes. In mountainous areas, frost wedging creates angular rock fragments that accumulate to form talus slopes. Figure 6.3 Ice breaks bottle. Smart Figure 6.4 Ice breaks rock. Smart Figure 6.4 Full alternative text description. For many years, the conventional wisdom was that most frost wedging occurred in this way. However, research has shown that frost wedging can also occur in a different way. It has long been known that when moist soils freeze, they expand, or frost heave, due to the growth of ice lenses. These masses of ice grow larger because they are supplied with water migrating from unfrozen areas as thin liquid films. As more water accumulates and freezes, the soil is heaved upward. A similar process occurs within the cracks and pore spaces of rocks. Lenses of ice grow larger as they attract liquid water from surrounding pores. The growth of these ice masses gradually weakens the rock, causing it to fracture. Bernard Hallett, Why Do Freezing Rocks Break? Science, 314, 1092, 1093, November 2006. Watch tutorial, Sheeting. Salt crystal growth. Another expansive force that can split rocks is created by the growth of salt crystals. Rocky shorelines and arid regions are common settings for this process. It begins when sea spray from breaking waves or salty groundwater penetrates crevices and pore spaces in rock. As this water evaporates, salt crystals form. As these crystals gradually grow larger, they weaken the rock by pushing apart the surrounding grains or enlarging tiny cracks. This same process can also contribute to the crumbling of roadways where salt is spread to melt snow and ice in winter. The salt dissolves in water and seeps into cracks that quite likely originated from frost action. When the water evaporates, the growth of salt crystals further breaks the pavement. Sheeting. When large masses of igneous rock, particularly granite, are exposed by erosion, concentric slabs begin to break loose. The process that generates these onion-like layers is called sheeting. It takes place, at least in part, due to the great reduction in pressure that occurs as the overlying rock is eroded away, a process called unloading. Figure 6. 5 illustrates what happens. As the overburden is removed, the outer parts of the granitic mass expand more than the rock below and separate from the rock body. Continued weathering eventually causes the slabs to separate and peel off, creating an exfoliation dome. Excellent examples of exfoliation domes are Stone Mountain, Georgia, and Half Dome and Liberty Cap in Yosemite National Park. Sheeting leads to the formation of an exfoliation dome. Smart Figure 6.5 Unloading leads to sheeting. Smart Figure 6.5 Full alternative text description. A process analogous to sheeting can also occur when human activities reduce the confining pressure, similar to what occurs during unloading. For example, in deep mines, large rock slabs have been known to explode off the walls of newly cut tunnels. In quarries, fractures occur parallel to the floor when large blocks of rock are removed. Watch tutorial, Ice Wedging. Although many fractures are created by expansion, others are produced by contraction during the crystallization of magma, and still others are produced by tectonic forces during mountain building. Fractures produced by these activities generally form a definite pattern and are called joints. Joints are important rock structures that allow water to penetrate to depth and start the process of weathering long before the rock is exposed. Aerial view of nearly parallel joints near Moab, Utah. Figure 6.6 Joints aid weathering. Biological activity. Weathering can be accomplished by the activities of organisms, including plants, burrowing animals, and humans. Plant roots in search of nutrients and water grow into fractures, and as the roots grow, they wedge apart the rock. Burrowing animals further break down rock by moving fresh material to the surface, where physical and chemical processes can more effectively attack it. Decaying organisms also produce acids that contribute to chemical weathering. Where rock has been blasted in search of minerals or for road construction, the impact of humans is particularly noticeable. Root wedging near Boulder, Colorado. Figure 6.7 Plants can break rock. Concept check 6.2. 1. When a rock is mechanically weathered, how does its surface area change? How does this influence chemical weathering? 2. Explain how water can cause mechanical weathering. 3. Describe how an exfoliation dome forms. 4. How do joints promote weathering? 5. How does biological activity contribute to weathering? 6.3 Chemical weathering. Discuss the importance of water and carbonic acid in chemical weathering processes. In the preceding discussion of mechanical weathering, you learned that breaking rock into smaller pieces aids chemical weathering by increasing the surface area available for chemical attack. It should also be pointed out that chemical weathering contributes to mechanical weathering. It does so by weakening the outer portions of some rocks, which, in turn, makes them more susceptible to being broken by mechanical weathering processes. Chemical weathering involves the complex processes that alter the internal structures of minerals by removing and/or adding elements. During this transformation, the original rock decomposes into substances that are stable in the surface environment. Consequently, the products of chemical weathering remain essentially unchanged as long as they remain in an environment similar to the one in which they formed. Did you know? The only common mineral that is very resistant to both mechanical and chemical weathering is quartz. The importance of water. Water is by far the most important agent of chemical weathering. Although pure water is non-reactive, a small amount of dissolved material is generally all that is needed to activate it. Oxidation. Everyone has seen iron and steel objects that have rusted when exposed to water. The same thing can happen to iron-rich minerals. The process of rusting occurs when oxygen combines with iron to form iron oxide, as follows. 4 Fe plus 3O2 oxygen 2 Fe2O3 iron oxide. This type of chemical reaction, called oxidation, occurs when electrons are lost from one element during the reaction. In this case, we say that iron was oxidized because it lost electrons to oxygen. Although the oxidation of iron progresses very slowly in a dry environment, the addition of water greatly speeds the reaction. Oxidation is important in decomposing such ferromagnesian minerals as olivine, pyroxene, hornblende, and biotite. Oxygen combines with the iron in these minerals to form the reddish-brown iron oxide called hematite, or in other cases a yellowish-colored rust called limonite. These products are responsible for the rusty color on the surfaces of dark igneous rocks, such as basalt, as they begin to weather. Hematite and limonite are also important cementing and coloring agents in many sedimentary rocks. Many sedimentary rocks are very colorful. The most important pigments are small amounts of iron oxide. Just as iron oxide colors the rusty barrels in A, this product of chemical weathering is also responsible for the reds and oranges seen in the rocks composing the Supai Formation in the Grand Canyon in B. Figure 6.8 Iron oxides add color. Carbonic acid. When carbon dioxide is dissolved in water, it forms carbonic acid, the same weak acid produced when soft drinks are carbonated. Rain dissolves some carbon dioxide as it falls through the atmosphere, and additional amounts released by decaying organic matter are acquired as the water percolates through the soil. Carbonic acid ionizes to form the very reactive hydrogen ion and the bicarbonate ion. Acids such as carbonic acid readily decompose many rocks and produce certain products that are water-soluble. For example, the mineral calcite, which composes the common building stones marble and limestone, is easily attacked by even a weakly acidic solution. The overall reaction by which calcite dissolves in water containing carbon dioxide is CaCO3 calcite plus carbonic acid Ca2 plus calcium IO plus 2HCO3 bicarbonation. During this process, the insoluble calcium carbonate is transformed into soluble products. In nature, over periods of thousands of years, large quantities of limestone are dissolved and carried away by groundwater. This activity is clearly evidenced by the large number of caverns found in all of the contiguous 48 states. Monuments and buildings made of limestone or marble are also subjected to the corrosive work of acids, particularly in urban and industrial areas that have smoggy, polluted air. The dissolving power of carbonic acid plays an important role in creating limestone caverns. This is an image of Berdine Cave in Croatia. Figure 6.9 Acidic waters create caves. How granite weathers. To illustrate how rock chemically weathers when attacked by carbonic acid, we will consider the weathering of granite, the most abundant continental rock. Recall that granite consists mainly of quartz and potassium feldspar. The weathering of the potassium feldspar component of granite takes place as follows. 2 KlC308 potassium feldspar plus 2 carbonic acid plus H2O water L2C2054 clay mineral plus 2K plus potassium ion plus 2 HCO3 bicarbonate ion plus 4 CO2 silica ion in solution. In this reaction, the hydrogen ions attack and replace potassium ions in the feldspar structure, thereby disrupting the crystalline network. Once the potassium is removed, it is available as a nutrient for plants or becomes the soluble salt potassium bicarbonate, which may be incorporated into other minerals or carried to the ocean in dissolved form by streams. The most abundant products of the chemical breakdown of feldspar are residual clay minerals. Clay minerals are the end products of weathering and are very stable under surface conditions. Consequently, clay minerals make up a high percentage of the inorganic material in soils. Moreover, the most abundant sedimentary rock, shale, contains a high proportion of clay minerals. In addition to the formation of clay minerals during the weathering of feldspar, some silica is removed from the feldspar structure and is carried away by groundwater. This dissolved silica will eventually precipitate to produce nodules of chert or flint, or it will fill in the pore spaces between sediment grains, or it will be carried to the ocean, where microscopic animals remove it from the water to build hard silica shells. To summarize, the weathering of potassium feldspar generates a residual clay mineral, a soluble salt, and some silica, which enters into solution. Quartz, the other main component of granite, is very resistant to chemical weathering and remains substantially unaltered when attacked by weak acidic solutions. As a result, when granite weathers, the feldspar crystals dull and slowly turn to clay, releasing the once interlocked quartz grains, which still retain their fresh, glassy appearance. Although some quartz remains in the soil, much is eventually transported to the sea or to other sites of deposition, where it becomes the main constituent of such features as sandy beaches and sand dunes. In time, these quartz grains may become lithified to form the sedimentary rock sandstone. Weathering of silicate minerals. Table 6.1 lists the weathered products of some of the most common silicate minerals. Remember that silicate minerals make up most of Earth's crust and that these minerals are composed essentially of only 8 elements. When chemically weathered, these silicate minerals yield sodium, calcium, potassium, and magnesium ions that form soluble products, which may be removed by groundwater. The element iron combines with oxygen, producing relatively insoluble iron oxides. Under most conditions, the 3 remaining elements, aluminum, silicon, and oxygen, join with water to produce residual clay minerals. However, even the highly insoluble clay minerals are very slowly removed by subsurface water. Table 6.1 Products of chemical weathering. Table 6.1 Full alternative text description. Spheroidal weathering. Many rock outcrops have a rounded appearance. This occurs because chemical weathering works inward from exposed surfaces. Figure 6.10 illustrates how angular masses of jointed rock change through time. The process is aptly called spheroidal weathering. Because weathering attacks edges from 2 sides and corners from 3 sides, these areas wear down faster than a single flat surface. Gradually, sharp edges and corners become smooth and rounded. Eventually, an angular block may evolve into a nearly spherical boulder. Once this occurs, the boulder's shape does not change, but the spherical mass continues to get smaller. Spheroidal weathering of extensively jointed rock. Smart Figure 6.10 Full alternative text description. Smart Figure 6.10 The formation of rounded boulders. Watch tutorial, Spheroidal weathering. Concept check 6.3. 1. How is carbonic acid formed in nature? 2. What occurs when carbonic acid reacts with calcite-rich rocks such as limestone? 3. What products result when carbonic acid reacts with potassium feldspar? 4. Explain how angular masses of rock often become spherical boulders. 6.4 Rates of weathering. Summarize the factors that influence the type and rate of rock weathering. We have already seen how mechanical weathering affects the rate of weathering. When rock is broken into smaller pieces, the amount of surface area exposed to chemical weathering increases. Other important factors that influence the type and rate of rock weathering include rock characteristics and climate. Rock characteristics. Rock characteristics encompass all the chemical traits of rocks, including mineral composition and solubility. In addition, any physical features, such as joints, can be important because they influence the ability of water to penetrate rock. The variations in weathering rates due to the mineral constituents can be demonstrated by comparing old headstones made from different rock types. Headstones of granite, which is composed of silicate minerals, are relatively resistant to chemical weathering. In contrast, marble headstones show signs of extensive chemical alteration over a relatively short period. We can see this by examining the inscriptions on the headstones shown in Figure 6.11. Marble is composed of calcite, which readily dissolves even in a weakly acidic solution. An examination of headstones in the same cemetery shows that the rate of chemical weathering is influenced by rock type. Smart Figure 6.11 Rock type influences weathering. Watch tutorial, Weathering rates. The silicates, the most abundant mineral group, chemically weather in essentially the same order in which they crystallize. By examining Bowen's reaction series, you can see that olivine crystallizes first and is therefore least resistant to chemical weathering, whereas quartz, which crystallizes last, is the most resistant. Climate. Climatic factors, particularly temperature and precipitation, are crucial to the rate of rock weathering. For example, the frequency of freeze-thaw cycles greatly affects the amount of frost wedging. Temperature and moisture also exert a strong influence on rates of chemical weathering and determine the kind and amount of vegetation present. Regions with lush vegetation often have a thick mantle of soil-rich and decayed organic matter from which chemically active fluids such as carbonic acid and various organic acids are derived. The optimum environment for chemical weathering is a combination of warm temperatures and abundant moisture. In polar regions, chemical weathering is ineffective because frigid temperatures keep the available moisture locked up as ice, whereas in arid regions there is insufficient moisture to promote rapid chemical weathering. Human activities often produce pollutants that alter the composition of the atmosphere. Such changes can, in turn, influence the rate of chemical weathering. One well-known example is acid rain. As a result of burning large quantities of coal and petroleum, tens of millions of tons of sulfur and nitrogen oxides are released into the atmosphere each year worldwide. Through a series of complex chemical reactions, some of these pollutants are converted into acids that then fall to Earth's surface as rain or snow. Figure 6.12 Acid rain accelerates the chemical weathering of stone monuments and structures. Differential weathering. Masses of rock do not weather uniformly. Take a moment to look back at the photo of Shiprock, New Mexico, in Figure 5.28. This durable volcanic neck protrudes high above the surrounding terrain. This phenomenon is called differential weathering. The results vary in scale from the rough, uneven surface of the marble headstone in Figure 6.11 to the boldly sculpted exposures of bedrock in New Mexico's Bisty Badlands. This example of differential weathering is in New Mexico's Bisty Badlands. When weathering accentuates differences in rocks, spectacular landforms are sometimes created. Smart Figure 6.13 Monuments to weathering. Differential weathering and subsequent erosion are responsible for creating many unusual, often spectacular rock formations and landforms. Many factors influence the rate of rock weathering. Among the most important are variations in the composition of the rock. More resistant rock protrudes as ridges or pinnacles, or as steeper cliffs on an irregular hillside. The number and spacing of joints can also be significant factors. Watch mobile field trip, Bisty Badlands. Did you know? The moon has no atmosphere, no water, and no biological activity. Therefore, the weathering processes we are familiar with on Earth are lacking on the moon. However, all lunar terrains are covered with a layer of gray debris, called lunar regolith, derived from a few billion years of bombardment by meteorites. The rate of change at the lunar surface is so slow that the footprints left by Apollo astronauts will likely remain fresh-looking for millions of years. Concept checks 6.4. 1. Explain why the headstones in Figure 6.11 have weathered so differently. 2. How does climate influence weathering? 6.5 Soil, an indispensable resource. Define soil and explain why soil is referred to as an interface. List and briefly discuss 5 controls of soil formation. Weathering is a key process in the formation of soil. Along with air and water, soil is one of our most indispensable resources. Also, like air and water, soil is often taken for granted. The following quote helps put this vital layer in perspective. Science, in recent years, has focused more and more on the Earth as a planet, one that for all we know is unique, where a thin blanket of air, a thinner film of water, and the thinnest veneer of soil combine to support a web of life of wondrous diversity and continuous change. Soil has accurately been called the bridge between life and the inanimate world. All life, the entire biosphere, owes its existence to a dozen or so elements that must ultimately come from Earth's crust. Once weathering and other processes create soil, plants carry out the intermediary role of assimilating the necessary elements and making them available to animals, including humans. When Earth is viewed as a system, as discussed in Chapter 1, soil is considered an interface, a common boundary where different parts of a system interact. This is an appropriate designation because soil forms where the geosphere, the atmosphere, the hydrosphere, and the biosphere meet. Soil is a material that develops in response to complex environmental interactions among different parts of the Earth system. Over time, soil gradually evolves to a state of equilibrium or balance with the environment. Soil is dynamic and sensitive to almost every aspect of its surroundings. Thus, when environmental changes occur, such as changes in climate, vegetative cover, and animal activity, the soil responds. Any such change gradually alters soil characteristics until a new balance is reached. Although thinly distributed over the land surface, soil functions as a fundamental interface, providing an excellent example of the integration among many parts of the Earth system. What is soil? With few exceptions, Earth's land surface is covered by regolith, a layer of rock and mineral fragments produced by weathering. Some would call this material soil, but soil is more than an accumulation of weathered debris. Soil is a combination of mineral and organic matter, water, and air, the portion of the regolith that supports the growth of plants. Although the proportions of the major components in soil vary, the same 4 components are always present to some extent. About 1/2 of the total volume of good quality surface soil is a mixture of disintegrated and decomposed rock and humus, the decayed remains of animal and plant life. The remaining half consists of pore spaces among the solid particles where air and water circulate. The pie chart depicts the composition of a soil in good condition for plant growth. Although percentages vary, each soil is composed of mineral and organic matter, water, and air. Figure 6.14 What is soil? Although the mineral portion of the soil is usually much greater than the organic portion, humus is an essential component. In addition to being an important source of plant nutrients, humus enhances the soil's ability to retain water. Because plants require air and water to live and grow, the portion of the soil consisting of pore spaces that allow these fluids to circulate is as vital as the solid soil constituents. Soil water is far from pure water. Instead, it is a complex solution that contains many soluble nutrients. Soil water not only provides the necessary moisture for the chemical reactions that sustain life, it also supplies plants with nutrients in a form they can use. The pore spaces that are not filled with water contain air. This air is the source of necessary oxygen and carbon dioxide for most microorganisms and plants that live in the soil. Did you know? Sometimes soils become buried and preserved. Later, if these ancient soils, called paleosols, are uncovered, they can provide useful clues to climates and the nature of landscapes thousands or millions of years ago. Controls of soil formation. Soil is the product of the complex interplay of several factors, including parent material, climate, plants and animals, time, and topography. Although all these factors are interdependent, their roles will be examined separately. Parent material. The source of the weathered mineral matter from which soils develop is called the parent material and is a major factor influencing newly forming soil. Gradually, this weathered material undergoes physical and chemical changes as soil formation progresses. Parent material can either be the underlying bedrock or a layer of unconsolidated deposits. When the parent material is bedrock, the soils are termed residual soils. By contrast, those developed on unconsolidated sediment are called transported soils. It should be pointed out that transported soils form in place on parent materials that have been carried from elsewhere and deposited by gravity, water, wind, or ice. The parent material for residual soils is the underlying bedrock. Transported soils form on unconsolidated deposits. Also note that as slopes become steeper, soil becomes thinner. Figure 6.15 Slopes and soil development. Figure 6.15 Full alternative text description. Parent material influences soils in two ways. First, the type of parent material influences the rate of weathering and thus the rate of soil formation. Also, because unconsolidated deposits are already partly weathered, soil development on such material will likely progress more rapidly than when bedrock is the parent material. Second, the chemical makeup of the parent material will affect the soil's fertility. This influences the character of the natural vegetation the soil can support. At one time, the parent material was thought to be the primary factor causing differences among soils. However, soil scientists have come to understand that other factors, especially climate, are more important. In fact, similar soils often develop from different parent materials, and dissimilar soils can develop from the same parent material. Such discoveries reinforce the importance of other soil-forming factors. Climate. Climate is considered to be the most influential control of soil formation. Temperature and precipitation are the elements that exert the strongest impact. As noted earlier in this chapter, variations in temperature and precipitation determine whether chemical or mechanical weathering will predominate and also greatly influence the rate and depth of weathering. For instance, a hot, wet climate may produce a thick layer of chemically weathered soil in the same amount of time that a cold, dry climate produces a thin mantle of mechanically weathered debris. Also, the amount of precipitation influences the degree to which various materials are removed from the soil by percolating water, thereby affecting soil fertility. Finally, climatic conditions are an important control on the type of plant and animal life present. Plants and animals. Plants and animals play a vital role in soil formation. The types and abundance of organisms strongly influence the physical and chemical properties of a soil. In fact, for well-developed soils in many regions, the significance of natural vegetation on soil type is frequently implied in the names used by soil scientists, such as prairie soil, forest soil, and tundra soil. Figure 6.16 Plants influence soil. The nature of the vegetation in an area can have a significant influence on soil formation. From left to right photos by Bill Brooks, Alamy Images, Nikolai Stanov, Shutterstock, and Elizabeth C. Domer, Shutterstock. Figure 6.16 Full alternative text description. Plants and animals furnish organic matter to the soil. Certain bog soils are composed almost entirely of organic matter, whereas desert soils might contain as little as a small fraction of 1%. Although the quantity of organic matter varies substantially among soils, it is a rare soil that completely lacks it. The primary source of organic matter in soil is plants, although animals and an infinite number of microorganisms also contribute. Decomposed organic matter supplies important nutrients to plants, as well as to animals and microorganisms living in the soil. Consequently, soil fertility is in part related to the amount of organic matter present. Furthermore, the decay of plant and animal remains causes the formation of various organic acids. These complex acids hasten the weathering process. Organic matter also has a high water-holding ability and thus aids water retention in a soil. Microorganisms, including fungi, bacteria, and single-cell protozoa, play an active role in the decay of plant and animal remains. The end product is humus, a material that no longer resembles the plants and animals from which it is formed. In addition, certain microorganisms aid soil fertility by converting atmospheric nitrogen into soil nitrogen. Earthworms and other burrowing animals act to mix the mineral and organic portions of a soil. Earthworms, for example, feed on organic matter and thoroughly mix soils in which they live, often moving and enriching many tons per acre each year. Burrows and holes also aid the passage of water and air through the soil. Time. Time is an important component of every geologic process, including soil formation. The nature of soil is strongly influenced by the length of time processes have been operating. If weathering has been going on for a comparatively short time, the character of the parent material strongly influences the characteristics of the soil. As weathering processes continue, the influence of parent material on soil is overshadowed by other soil-forming factors, especially climate. The amount of time required for various soils to evolve cannot be listed because the soil-forming processes act at varying rates under different circumstances. However, as a rule, the longer a soil has been forming, the thicker it becomes and the less it resembles the parent material. Topography. The lay of the land can vary greatly over short distances. Variations in topography can lead to the development of a variety of localized soil types. Many of the differences exist because the length and steepness of slopes significantly affect the amount of erosion and the water content of soil. On steep slopes, soils are often poorly developed. Due to rapid runoff, the quantity of water soaking in is slight. As a result, the moisture content of the soil may not be sufficient for vigorous plant growth. Further, because of accelerated erosion on steep slopes, the soils are thin or in some cases non-existent. In contrast, poorly drained and waterlogged soils found in bottomlands have a much different character. Such soils are usually thick and dark. The dark color results from the large quantity of organic matter that accumulates because saturated conditions retard the decay of vegetation. The optimum terrain for soil development is a flat to undulating upland surface. Here we find good drainage, minimum erosion, and sufficient infiltration of water into the soil. Slope orientation, or the direction a slope is facing, is another consideration. In the mid-latitudes of the northern hemisphere, a south-facing slope receives a great deal more sunlight than a north-facing slope. In fact, a steep north-facing slope may receive no direct sunlight at all. The difference in the amount of solar radiation received causes differences in soil temperature and moisture, which in turn influence the nature of the vegetation and the character of the soil. Although this section deals separately with each of the soil-forming factors, remember that all of them work together to form soil. No single factor is responsible for a soil's character, rather, it is the combined influence of parent material, climate, plants and animals, time, and topography that determines a soil's character. Did you know? It usually takes between 80 and 400 years for soil-forming processes to create 1 centimeter of topsoil. Concept check 6.5. 1. Explain why soil is considered an interface in the Earth system. 2. How is regolith different from soil? 3. List the 5 basic controls of soil formation. 4. Which factor is most influential in soil formation? 5. How might the direction a slope is facing influence soil formation? Jack Eddy, A Fragile Seam of Dark Blue Light, in Proceedings of the Global Change Research Forum. U.S. Geological Survey Circular 1086, 1993, page 15. 6.6 Describing and classifying soils. Sketch, label, and describe an idealized soil profile. Explain the need for classifying soils. The factors controlling soil formation vary greatly from place to place and from time to time, leading to an amazing variety of soil types. The soil profile. Because soil-forming processes operate from the surface downward, soil composition, texture, structure, and color gradually evolve differently at varying depths. These vertical differences, which usually become more pronounced as time passes, divide the soil into zones or layers known as horizons. If you were to dig a pit in soil, you would see that its walls are layered. Such a vertical section through all of the soil horizons constitutes the soil profile. Figure 6.17 presents an idealized view of a well-developed soil profile in which 5 horizons are identified. From the surface downward, they are designated as O, A, E, B, and C. These 5 horizons are common to soils in temperate regions. Idealized soil profile from a humid climate in the middle latitudes. Smart Figure 6.17 Full alternative text description. Smart Figure 6.17 Soil horizons. The O soil horizon consists largely of organic material. In contrast, the layers beneath it consist mainly of mineral matter. The upper portion of the O horizon is primarily plant litter, such as loose leaves and other organic debris that is still recognizable. By contrast, the lower portion of the O horizon is made up of partly decomposed organic matter in which plant structures can no longer be identified. In addition to plants, the O horizon is teeming with microscopic life, including bacteria, fungi, algae, and insects. All these organisms contribute oxygen, carbon dioxide, and organic acids to the developing soil. The A horizon is largely mineral matter, yet biological activity is high, and humus is generally present, up to 30% in some instances. Together the O and A horizons make up what is commonly called the topsoil. The E horizon is a light-colored layer that contains little organic material. As water percolates downward through this zone, finer particles are carried away. This washing out of fine soil components is termed alluviation. Water percolating downward also dissolves soluble inorganic soil components and carries them to deeper zones. This depletion of soluble materials from the upper soil is termed leaching. The B horizon, or subsoil, is where much of the material removed from the E horizon by alluviation is deposited. Thus, the B horizon is often referred to as the zone of accumulation. The accumulation of the fine clay particles enhances water retention in this horizon. In extreme cases, clay accumulation can form a very compact and impermeable layer called hardpan. Watch tutorial, Soil Horizons. The O, A, E, and B horizons together constitute the solemn, or true soil. It is in the solemn that the soil-forming processes are active and that living roots and other plant and animal life are largely confined. The C horizon is characterized by partially altered parent material. Whereas the parent material is difficult to see in the O, A, E, and B horizons, it is easily identifiable in the C horizon. Although this material is undergoing changes that will eventually transform it into soil, it has not yet crossed the threshold that separates regolith from soil. Not all soils have these 5 layers. The characteristics and extent of horizon development vary in different environments. Thus, different localities exhibit soil profiles that can contrast greatly with one another. The boundaries between soil horizons may be sharp, or the horizons may blend gradually from one to another. Consequently, a well-developed soil profile indicates that environmental conditions have been relatively stable over an extended time span and that the soil is mature. By contrast, some soils lack horizons altogether. Such soils are called immature because soil building has been going on for only a short time. Immature soils are also characteristic of steep slopes, where erosion continually strips away the soil, preventing full development. Soil characteristics and development vary greatly in different environments. Figure 6.18 Contrasting soil profiles. Classifying soils. To understand the great variety of soils on Earth scientists needed to devise some means of classifying the vast array of soil data. Establishing categories of items having certain important characteristics in common introduces order and simplicity, which not only aids comprehension and understanding but also facilitates analysis and explanation. Soil scientists in the United States have devised a system for classifying soils known as the soil taxonomy. It emphasizes the physical and chemical properties of the soil profile and is organized on the basis of observable soil characteristics. There are 6 hierarchical categories of classification, ranging from order, the broadest category, to series, the most specific category. The system recognizes 12 soil orders and more than 19,000 soil series. The names of the classification units are mostly combinations of Latin or Greek descriptive terms. For example, soils of the order Aridisol are characteristically dry soils in arid regions. Soils in the order Inceptisol are soils with only the beginning, or inception, of profile development. Table 6.2 provides brief descriptions of the 12 basic soil orders. Figure 6.19 shows the complex worldwide distribution pattern of the soil taxonomy's 12 soil orders. Like many other classification systems, the soil taxonomy is not suitable for every purpose. It is especially useful for agricultural and related land use purposes, but it is not a useful system for engineers who are preparing evaluations of potential construction sites. Table 6.2 Basic soil orders. Table 6.2 Full alternative text description. Worldwide distribution of the soil taxonomy's 12 soil orders. Points A and B are references for a give it some thought item at the end of the chapter. Figure 6.19 Global soil regions. Figure 6.19 Full alternative text description. Concept checks 6.6. 1. Sketch and label the main soil horizons in a well-developed soil profile. 2. Describe the following features or processes: alluviation, leaching, zone of accumulation, and hardpan. 3. Why are soils classified? 4. Refer to Figure 6.19 and identify 3 particularly extensive soil orders that occur in the contiguous 48 United States. Describe 2 soil orders in Alaska. 6.7 The impact of human activities on soil. Explain the detrimental impact of human activities on soil. Soils are just a tiny fraction of all Earth materials, yet they are vital. Soils are necessary for the growth of rooted plants and thus are a basic foundation of the human life support system. Because soil forms very slowly, it must be considered a non-renewable resource. Just as human ingenuity can increase the agricultural productivity of soils through fertilization and irrigation, soils can be damaged or destroyed by careless activities. Despite their role in providing food, fiber, and other basic materials, soils are among our most abused resources. Clearing the tropical rainforest, a case study of human impact on soil. Over the past few decades, the destruction of tropical forests has become a serious environmental issue. Each year, millions of acres are cleared for agriculture and logging. This clearing results in soil degradation, loss of biodiversity, and climate change. The thick soils of the Amazon rainforest in Suriname are highly leached. Clearing the tropical rainforest is a serious environmental problem. Figure 6.20 Tropical deforestation. Thick red-orange soils are common in the wet tropics and subtropics. They are the end product of extreme chemical weathering. Because lush tropical rainforests are associated with these soils, many people assume that they are fertile and have great potential for agriculture. However, just the opposite is true. Oxisols are among the poorest soils for farming. How can this be? Rainforest soils develop under conditions of high temperature and heavy rainfall, and they are therefore severely leached. Not only does leaching remove the soluble materials such as calcium carbonate, but the great quantities of percolating rainwater also remove much of the silica, and as a result, insoluble oxides of iron and aluminum become concentrated in the soil. Iron oxides give the soil its distinctive color. Because bacterial activity is high in the wet tropics, organic matter quickly breaks down, so rainforest soils contain very little humus. Moreover, leaching destroys fertility because most plant nutrients are removed by the large volume of downward percolating water. Therefore, despite the dense and luxuriant vegetation, the soil itself contains few available nutrients. Most nutrients that support the rainforest are locked up in the trees. As vegetation dies and decomposes, the roots of the rainforest trees quickly absorb the nutrients before they are leached from the soil. The nutrients are continuously recycled as trees die and decompose. Therefore, when forests are cleared to provide land for farming or to harvest timber, most of the nutrients are removed as well. What remains is a soil that contains little to nourish planted crops. Rainforest clearing not only removes plant nutrients but also accelerates soil erosion. The roots of rainforest vegetation anchor the soil, and leaves and branches provide a canopy that protects the ground by deflecting the full force of the frequent heavy rains. When the protective vegetation is gone, soil erosion increases. The removal of vegetation also exposes the ground to strong direct sunlight. When baked by the sun, these tropical soils can harden to a brick-like consistency and become practically impenetrable to water and crop roots. In just a few years, a freshly cleared area may no longer be cultivable. Soil erosion, losing a vital resource. Many people do not realize that soil erosion, the removal of topsoil, is a serious environmental problem. Perhaps this is the case because a substantial amount of soil seems to remain even where soil erosion is serious. Nevertheless, although the loss of fertile topsoil may not be obvious to the untrained eye, it is a significant and growing problem as human activities expand and disturb more and more of Earth's surface. Soil erosion is a natural process. It is part of the constant recycling of Earth materials that we call the rock cycle. Once soil forms, erosional forces, especially water and wind, move soil components from one place to another. Every time it rains, raindrops strike the land with surprising force. Each drop acts like a tiny bomb, blasting movable soil particles out of their positions in the soil mass. Then, water flowing across the surface carries away the dislodged soil particles. Because the soil is moved by thin sheets of water, this process is termed sheet erosion. Soil dislodged by raindrop impact is more easily moved by sheet erosion. Figure 6.21 Full alternative text description. Figure 6.21 Raindrop impact. After the water flows as a thin, unconfined sheet for a relatively short distance, threads of current typically develop, and tiny channels called rills begin to form. Still deeper cuts in the soil, known as gullies, are created as rills enlarge. When normal farm cultivation cannot eliminate the channels, we know the rills have grown large enough to be called gullies. Although most dislodged soil particles move only a short distance during each rainfall, substantial quantities eventually leave the fields and make their way downslope to a stream. Once in the stream channel, these soil particles, which can now be called sediment, are transported downstream and eventually deposited. A. Sheet flow and rills. B. Rills can grow into deep gullies. Figure 6.22 Full alternative text description. Figure 6.22 Soil erosion on unprotected soils. Rates of erosion. We know that soil erosion is the ultimate fate of practically all soils. In the past, erosion occurred at slower rates than it does today because more of the land surface was covered and protected by trees, shrubs, grasses, and other plants. However, human activities such as farming, logging, and construction, which remove or disrupt the natural vegetation, have greatly accelerated the rate of soil erosion. Without the stabilizing effect of plants, the soil is more easily swept away by the wind or carried downslope by sheet wash. Did you know? It has been estimated that between 3 and 5 million acres of prime U.S. farmland are lost each year through mismanagement and conversion to non-agricultural uses. According to the United Nations, since 1950 more than one-third of the world's farmable land has been lost to soil erosion. Natural rates of soil erosion vary greatly from one place to another and depend on soil characteristics as well as factors such as climate, slope, and type of vegetation. Over a broad area, erosion caused by surface runoff may be estimated by determining how much sediment is carried by the streams that drain the region. Studies of this kind made on a global scale indicate that prior to the appearance of humans, sediment transport by rivers to the ocean amounted to just over 9 billion metric tons per year. In contrast, the amount of material currently transported to the sea by rivers is about 24 billion metric tons per year, or more than 2.5 times the earlier rate. It is estimated that flowing water is responsible for about 2/3 of the soil erosion in the United States. Much of the remainder is caused by wind. When dry conditions prevail, strong winds can remove large quantities of soil from unprotected fields. At present, it is estimated that topsoil is eroding faster than it forms on more than one-third of the world's croplands. The results are lower productivity, poorer crop quality, reduced agricultural income, and an ominous future. When the land is dry and largely unprotected by anchoring vegetation, soil erosion by wind can be significant. Figure 6.23 Wind erosion. The 1930s Dust Bowl. During the 1930s, large dust storms plagued the Great Plains. Because of the size and severity of these storms, the region came to be called the Dust Bowl, and the time period was called the Dirty Thirties. The heart of the Dust Bowl was nearly 100 million acres in the panhandles of Texas and Oklahoma and adjacent parts of Colorado, New Mexico, and Kansas. At times, dust storms were so severe that they were called black blizzards and black rollers because visibility was sometimes reduced to only a few feet. Dust blackens the sky near Elkhart, Kansas, on May 21, 1937. Large dust storms like this one stripped topsoil from large parts of the Great Plains during the dry 1930s. In places, dust drifted like snow, covering farm buildings, fences, and fields. Figure 6.24 1930s Dust Bowl. Figure 6.24 Full alternative text description. What caused the Dust Bowl? Clearly, the fact that portions of the Great Plains experience some of North America's strongest winds is important. However, it was the expansion of agriculture during an unusually wet period that set the stage for the disastrous period of soil erosion. Mechanization allowed the rapid transformation of the grass-covered prairies of this semi-arid region into farms. As long as precipitation was adequate, the soil remained in place. However, when a prolonged drought struck in the 1930s, the unprotected soils were vulnerable to the wind. Severe soil loss, crop failure, and economic hardship resulted. Controlling soil erosion. On every continent, unnecessary soil loss is occurring because appropriate conservation measures are not being taken. Although it is a recognized fact that soil erosion can never be completely eliminated, soil conservation programs can substantially reduce the loss of this basic resource. Steepness of slope is an important factor in soil erosion. The steeper the slope, the faster the water runs off and the greater the erosion. It is best to leave steep slopes undisturbed. When such slopes are farmed, terraces can be constructed. These nearly flat, step-like surfaces slow runoff and thus decrease soil loss while allowing more water to soak into the ground. Soil erosion by water also occurs on gentle slopes. Figure 6.25 illustrates one conservation method in which crops are planted parallel to the contours of the slope. This pattern reduces